Welcome to the public exam review on Chapter 8, dealing with logarithmic functions. In this presentation, we will look at the transformations of logarithmic functions. In Part 1, we will focus on explaining the effects of the parameters a, b, h, and k in the equation y equals a times the log of b outside of x minus h to base c plus k. And we will study the effects of those parameters on the graph of y equals the log of x to base c. For the purposes of this unit, the value of c will always be greater than 1. Before we begin looking at transformations, let's review how to graph a logarithmic function in the form of y equals the log of x to base c. First, we will graph y equals the log of x to base 3. In order to graph that function, you need to convert it to exponential form. So in exponential form, we would have 3 raised to the power of y is equal to x. Notice here that y is the independent variable, x is a dependent variable since it depends upon what the value of y is. So we will assign a couple of negative values to y, 0, and a couple of positive values to y in order to determine the value of x. So when y is a negative 2, 3 raised to the power of negative 2 is the same as 1 over 3 squared. So the value of x is 1 over 9. In order to plot that point on the graph, we go very close to the right side of the y-axis, where x is approximately 1 over 9 and a negative 2. When y is a negative 1, 3 raised to the power of negative 1 is 1/3. So we have the point 1/3 and negative 1. When y is 0, 3 raised to the power of 0 is equal to 1. So the point 1 and 0 is on the base graph of the log of x to base 3. When y is equal to 1, 3 raised to the power of 1 is 3. So the coordinates 3 and 1 are on the new function. And as well, when y is equal to 2, 3 squared is equal to 9. So the point 9 and 2 is on the graph of this logarithmic function. So the shape of a logarithmic function where the value of c is greater than 1 is given in that graph. The domain of this function, if you literally put your finger on the x-axis, notice that all values of x are greater than 0. So the domain would be all values of x such that x is greater than 0, but x belongs to the set of real numbers. The range involves the possible values for y, and no matter what value of y you get, you will always get a point that corresponds to this graph. So the range will involve all values of y belonging to the set of real numbers. Notice that the graph itself will approach this vertical axis here, namely the y-axis. So we have what is called a vertical asymptote for this graph. And the vertical asymptote is given by the equation x equals 0, which is the equation for your y-axis. What we will do now is we will take the base graph of y equals the log of x to base 3. So I've just chosen a base 3 logarithm here. You could have chosen any other base such that the base could have been 2 or 4 or 5, whatever you want to choose. But in this case, we will limit the transformations to the log of x to base 3. First, we will look at vertical and horizontal reflections. Notice that the black graph that I have drawn here is the graph of y equals the log of x to base 3. And I've included the table of values over here to the right so that you can see what points come from the base graph. The first thing that we notice here is that the point 9 and 2 is highlighted there in the base graph, and that point has been transformed to 9 and negative 2. We will talk about the domain and the range of the green graph that you see there, which is the transform graph. Note that all values of x are still greater than 0, and x belongs to the set of reals. The range will be any real number. So we have y belonging to the set of real numbers, and the vertical asymptote is still the y-axis, which is x equal to 0. The mapping rule, however, you have xy that comes from the base graph, and notice that the values of x stay the same, but the y value becomes negative. So y gets transformed to a negative y. In order to determine the equation of the transform graph, we have y equals, so you can see there that there has been what we call a vertical reflection in the x-axis. So the equation that corresponds with this graph will be a negative in front of the log of x to base 3. Let's look at the other example. Note that from the base graph, we have the point 9 and 2 is transformed to negative 9 and 2. The domain of that green graph that you see there are all values of x that are less than 0 this time, and x belongs to the set of reals. The range did not change. We still have the values of y belonging to the set of real numbers. The vertical asymptote is still the y-axis, so the equation would be x equals 0. However, the mapping rule this time takes xy from your base equation and it gets mapped onto a negative x and y. This happens whenever we see a horizontal reflection in the x-axis. And in the equation, we will see it written as y equals the log of a negative x to base 3. So then, what parameter is affected here if we look at the base equation of y equals a times the log of b outside of x minus h to base c plus k? The effect of the parameters a and b, if it's a vertical reflection, then we must know that the value of a has to be negative. A has to be less than 0 if there's a vertical reflection in the x-axis. A horizontal reflection will occur when the value of b is less than 0. And then there will be a horizontal reflection in the y-axis. Let's look at the vertical and horizontal stretches. Using the graphs that you see here, we have the base graph of y equals the log of x to base 3. We will still use a transformation of that base graph. Here's the equation, and this is the corresponding table of values. So note in this example that the point 9 and 2 is transformed to 9 and 8. That results in a vertical stretch equal to 4, because 2 multiplied by 4 equals 8. The domain of the green graph will be all values of x that are greater than 0. X belongs to the set of reals. The range involves any real number. The vertical asymptote is still the y-axis where x is equal to 0. But this time, note that the mapping rule for this function takes xy from your base graph. We keep x the same, but this time you're going to multiply the original y value by 4. So you get 4y. And the equation will look like y equals 4 multiplied by the log of x to base 3. So we see here that the coefficient, the number in front of the log, represents a vertical stretch equal to 4. Let's look at the second example. On the base graph, we take the point 3 and 1, and on the green graph, that's mapped onto 6 and 1. Notice that the y-coordinates remain the same. So what's happening in this example is we have a horizontal stretch equal to 2. The original x value, when multiplied by 2, gives us 6, and the y-coordinates stay the same. The domain in this case are all values of x greater than 0, where x belongs to the set of real numbers. Notice that a horizontal or a vertical reflection, nor a horizontal or a vertical stretch has affected the domain of the function for the most part. Unless it was a horizontal reflection, then it became x less than 0. The range, on the other hand, are all values of y belonging to the set of reals. The vertical asymptote is still your y-axis, where x is equal to 0. Our mapping rule takes xy from the base graph, and that got mapped onto 2x, and you keep y the same. The equation this time, though, will be given by y equals the log of. If we have a horizontal stretch of 2, remember that you have to use the reciprocal of 2, which is 1/2 in front of the x, and that will be to a base of 3. So for a vertical stretch, the coefficient will just be the value of a. In the case of a horizontal stretch, the coefficient of your x term will be the reciprocal of your horizontal stretch. So in terms of the effects of the parameters a and b, in this case, your vertical stretch will always equal the absolute value of a. All right, we have to use absolute value just in case a is negative, which represents a reflection. Similarly, the horizontal stretch will always equal the reciprocal, so it will be 1 over the absolute value of b, just in case there's a horizontal reflection in the y-axis. So let's continue with the horizontal and the vertical translations. Notice here that the original point 1, 0 on the base graph is now transformed to 1 and a -4. And you can see there that the entire original graph has been shifted downward by 4 units. So we have a vertical translation here equal to a -4, meaning that the base graph is shifted or translated down 4 units. The domain will be all values of x greater than 0, where x belongs to the set of reals. The range are all values of y belonging to the set of real numbers. The vertical asymptote is still the y-axis, where x is equal to 0. But this time your mapping rule, xy, takes all points from your original graph and it transforms it to x, and that will be y. If it's a translation of 4 units down, it will be y -4. Sorry, that will be y plus 4. Vertical translation of 4 units down, so we have y -4 in the mapping rule. So in your equation then, that will be given by y equals the log of x to base 3, and then because it's shifted 4 units down, we have -4 at the end. In the second graph, this represents a horizontal translation. So we take the point at 1, 0, and notice that that is transformed to the point -1 and 0. So what we have here is a horizontal translation equal to a -2 units to the left. The domain, this time, notice that all values of x are greater than a -2, where x belongs to the set of real numbers. The range are all values of y belonging to the set of real numbers, but this time we have a new vertical asymptote. And if I could just sketch that in there to illustrate what I'm talking about, we have a vertical asymptote that passes through x equals a -2. So the original vertical asymptote, which was the y-axis, is now shifted 2 units to the left as well. So you have a vertical asymptote through x equals a -2. So that is the equation of your vertical asymptote, and your mapping rule takes xy from your original graph, and it will be transformed to x -2 because it's going to the left, and you keep y the same. So the equation this time will be y equals the log of, that will be x plus 2 to base 3, and that represents a horizontal translation equal to a -2 units to the left, We use opposites of reciprocals when you're dealing with horizontal transformations. So now, the effects of the parameters h and k. In order for you to have a vertical translation, the value of k, if k is greater than 0, you move upward. If k is less than 0, the original graph moves downward. If h is greater than 0, the original graph moves to the right, and if h is less than 0, the original graph moves to the left. Let's look at some examples. Here we are asked, which equation represents the graph? Here we have the log of x is equal to y minus 3, the log of x equals y plus 3, and so on. What we need to do with each of these equations is change them to solve for y. So we would have y equals the log of x plus 3. In the second example, we would have y equals the log of x minus 3. In the third, we have y equals the log of x plus 5. And in the last one, we have y equals the log of x minus 5. Note that the original logarithmic function would pass through the point 1 and 0. So no matter what the graph would be here, in this case here, that would be the graph of y equals the log of x by itself to base 10 if there's no base given. So that would be the point 10 and 1 here, and the point 1 and 0. If you have a vertical translation of 3 units upward, and it's obvious that we have a vertical translation upward to get from one graph to the other. So there is a vertical translation upward, but just how far do we go? So because it goes upward, you can eliminate B and D as multiple choice answers because both of these have vertical translations downward. So have we moved 3 units upward or have we moved 5 units upward? If we have moved 3 units upward, then the point 1, 0 should be moved to the point 1 and 3. So you can see there that the original point on the base graph, 1 and 0, goes to the point 1 and 3. So we have a vertical translation here equal to 3. Therefore, the equation must be y equals the log of x plus 3, and this corresponds with A as the multiple choice answer. In example number 2, which translations occur when the graph of y equals the log of x to base 4 is transformed to y equals the log of 3x minus 6 to base 4 minus 5? In this case, we need to do some work with the horizontal stretch and the horizontal translation inside those brackets. So to rearrange that equation, we will have y equals the log of 3 outside of x minus 2 to base 4 minus 5. So now when we're talking about the translations that occur, you can see here that we have a horizontal translation equal to 2 units to the right because the value of h is positive. Here we would have a vertical translation equal to -5 units downward. And that's when we're making the comparison using the parameters where we have y equals the log of b outside of x minus h plus k. And that would be to whatever the base of c is. So in this case here, the value of h is positive. So you move 2 units to the right. Here the value of k is negative, which means we move 5 units downward. So this answer then corresponds with C as your multiple choice answer. In example 3, which equation results when y equals the log of x is transformed using the mapping rule? So this time we have to go from the mapping rule to the equation. Notice that no base is given. So we understand that to be a common logarithm with a base of 10. So here we have y equals, now when there is no coefficient here for the y value. So that means that there is no vertical stretch occurring. So we will just have y equals the log of, and whatever the base is will be base 10 this time. However, when you're dealing with the x values, we have to use opposites and reciprocals. So here I see a -1/2. So the reciprocal of that is a -2. Then I see x plus 1. So that will be written as x minus 1. Just let me fix that a bit. So that would be written as x minus 1 in the equation. And then you have y minus 12, so you just simply subtract 12 at the end. So let's verify that again. So the mapping rule would take xy from the base graph of y equals the log of x. And you have it mapped onto a -1/2 x plus 1, because we use the reciprocal and we use the opposite. So the reciprocal of a -2 is a -1/2. And the opposite of x plus 1 is x minus 1. And then the y minus 12 at the end represents the vertical translation of 12 units downward. So this answer then corresponds with A as the multiple choice answer. And finally, in example 4, we are asked, which is the graph of y equals the log of b times x minus h to base c if c is greater than 1, if b is less than 0, and if h is less than 0. Well, first of all, if b is less than 0, that represents a horizontal reflection in the y-axis. So if we start off with a base graph, I'm just going to sketch any graph where the value of c is greater than 1. So if we start off with this as a base graph, remember that the point 1, 0 will lie on all of these functions of this form. So that's just simply the graph of y equals the log of x to any base c. So now, if b is less than 0 and we have a horizontal reflection in the y-axis, then the point 1, 0 will get mapped onto the point -1 and 0. So this is the graph that results when b is less than 0. But then we have the value of h is less than 0. So if h is less than 0, that results in a horizontal translation to the left. So it means that and we don't know how many units to the left, just that the vertical asymptote will then be over here to the left side, and your graph will be shifted over this way as well. So this is the graph that results when h is less than 0. And this green graph that you see corresponds with A as your multiple choice answers. As a summary then, we are talking about the effects of the parameters a, b, h, and k in the equation where we have y equals a times the log of b times x minus h to base c plus k. And we talk about that as on the graph of a transformation of the graph of the log function y equals the log of x to base c. So A represents the vertical stretch. We have a vertical stretch equal to the absolute value of A, which reminds us that a vertical stretch is never negative. When A is less than 0, that will result in a vertical reflection in the x-axis. Similarly for the parameter B. The parameter B tells us that we have a horizontal stretch which is equal to 1 over the absolute value of B. Remember that a horizontal stretch can never be negative. So when the value of B is less than 0, that results in a horizontal reflection in the y-axis. H involves a horizontal translation of H units. If H is greater than 0, you move to the right. If H is less than 0, the base graph moves to the left. The parameter K involves a vertical translation of k units. Similarly, if k is greater than 0, your base graph moves up, and if k is less than 0, your base graph moves downward. In part 2 of this presentation, we will take the graph of a logarithmic function and we will use mapping rules to perform the transformations. So that's in the next presentation on the transformation of logarithmic functions, part 2. Thank you.